I will put your key to this exam on D2L. I have it, but I think I didn't bring it tonight, so. We can go over any of the problems you want. Let's see, Ronan Life, are you here? Here we go. Tyler Trulock. Tyler?
He's gonna be here in just a second.
Okay, Austin Segrist. Okay. Tyler, hand up.
And an off page.
Here's, Eli.
Much good.
Okay. The team, Jack Taylor here. Brandon Duffner. Okay. Malay. Did I pronounce your last name correctly? Sorry. Pentagraph. Padel. Haley Smith. Jesus Estrada. Jackson Granger. Jackson. Rena Bryant. Miyaki Higuchi. Brad Bose. Langston Chen. Benjamin Rodriguez. Benjamin. Daniel Starks. What I missed?
I wasn't here on Wednesday.
Okay, then we need to talk about making up the exam. Maybe I'll tell you what, I'll put the key online till Wednesday and I'll talk to you after class. Let's see. Last time I had somebody go out of the room for the thing, I forgot to bring them back in. It's so awful. Well, maybe I should do that anyway, but why don't you come back in 10 minutes? Does that sound good? Now let's go over some of the problems and then that'll work about right. Thank you. Okay, particularly like to see off the exam, we'll go over some of these. Like I said, I'll put the key online. So.
We do 4A.
Okay. Probably a number of these I'd like to do. We didn't do as well on this as I'd hoped. There were a bunch of really high scores and then a bunch of really low scores, and I don't know what to make. So 4A, this is a good one to do. This on the sum k equals to infinity. -1 to the k plus 1. X plus 2. A lot of you don't have to get started on this one. I had trouble finishing. X plus 2 to the 2k plus 1 over 4 to the k. And it was find the radius of convergence. And interval of convergence. Let's see, what was your name, Ms. Kinnan? Ahmed, did you take the exam lesson?
Yes, Professor, I have to register for that.
Okay, why don't you wait just for a few minutes because we're gonna go over a few of the problems.
Okay,
Okay,
after the class or?
yeah, come back about 10 minutes.
Okay.
Okay, yeah, sorry about that. Okay, on this one, we said, since we have these powers here, it's nice to use the ratio test and let rho be the limit of as k goes to infinity, the quotient of consecutive terms. So you take minus one, replace k by k plus one, and you get minus one to the k plus one times the x plus two to the twice k plus one over four to the k plus one. That's the k plus first term. Then you divide that by the kth term, minus one to the k plus one, x plus two to the two k plus one over four to the k. So there's the ratio of the k plus first term to the kth. So we're looking at the ratio test. Now you take top times bottom over middle times middle to evaluate that. And get 4 to the k. These go away because of the absolute value. You don't care about those. 4 to the k times this, x plus 2 to the 2k plus 3 over middle times middle, 4 to the k plus 1 times x plus 2 to the 2k plus 1. And absolute value still. And now the 4 to the k cancels 4 to the k here, is left with 4 on the bottom. And x plus 2 to the 2k plus 3 over x plus 2 to the 2k plus 1 leaves x plus 2 squared. Now that's the ratio. Now k is gone out of there, right? So the limit of this is treated as a constant since there's no k in there. This is just x plus 2 squared over 4. So that's the ratio of consecutive terms. At any x, you get this value. So for convergence, we need rho less than 1. X plus 2 squared over 4 less than 1. A lot of people got to about here and just had difficulty telling what to do. You write that equivalently as x plus 2 squared less than 4, which is equivalent to an absolute value of x plus 2 less than 2 by square rooting. Right, the square root of the square is the absolute value. And now this says, right, this is the distance between 2 and x. So this is x is less than 2. So x has to be within 2 units the radius of the point minus 2. So x0 is minus 2, is what's subtracted in here. And you go 2 units on each side. So it's minus 4 less than x less than 0. Now, we didn't check the endpoints. You have to check the endpoints separately to make sure you got the whole interval. So that x equals -4, you plug that in and see what you get. Sum minus 1 to the k plus 1. Minus 4 plus 2 is minus 2. So minus 4 to the 2k plus 1, so you got minus 2 to the 2k plus 1 over 4 to the k. Well, minus 2 to the 2k is 4 to the k. So you can cancel the 4 to the k with the minus 2 to the 2k, and this just becomes minus 2 sum minus 2 times minus 1 to the k plus 1. Well, that doesn't converge because the limit as k goes to infinity, the k term is at 0, right? So this diverges by the divergence test. The terms aren't getting smaller and smaller. They're all plus 2, minus 2, plus 2, minus 2. And then you check the other point also at x equals 0, you get the same thing. So we'll say also at x equals 0, same series as divergence. Consequently, this is the whole interval. You have to check the endpoints. Sometimes it includes the endpoints. But there's the interval, and here's the radius, r equals 2. That was maybe the hardest problem. I think 1A gave a little trouble too. To decide whether this is absolutely convergent. Definitely convergent or divergent, you take minus 1 to the k over k, natural log k. A running from 2 to infinity. You first try for absolute convergence. If it converges absolutely, you're done. It's not being checked for if it converges without requiring absolute convergence. And if that happens, then you've got conditional convergence. So let's check the series of absolute values. What about sum 1 over k times ln k? This is the series of absolute values. Does that converge? Well, you notice that this, if I just call it x instead of k and integrate it from 1 to infinity, I can do that integral. So I can apply the integral test for a series with positive terms. Just make 2, sorry. And this goes from 2 to infinity. Series with positive terms, you can look at the corresponding integral. And if this is a continuous, decreasing function that interpolates the points positive, then you can do the corresponding integral. And they both converge or both diverge. So we can see if this one converges by whether this one converges. And this one we know how to do. You let u equal natural log of x. And by the way, it doesn't have to be decreasing forever. It has to be eventually decreasing. It's all right if this increases for a while. Because you can drop out any finite number of terms from this and then just start farther down. And as long as it's eventually beginning at some finite point, continuous and decreasing and positive, and continuous before that so you can integrate it, then you can still apply the integral test. It just has to be eventually continuous, decreasing, and positive, beginning at some number, no matter how large. So that might be the case here. I'm not sure from 2 to 3 if it decreases or not, but we'll apply the integral test. And if you take u equal ln of x, then du 1 over x dx. Oh, and this 1 over x dx is sitting right there. So that's a good substitution. This is du, this is u. This becomes integral 1 over u du, right? And instead of starting at 2, when x equals 2, u equals ln of 2. So the integral over u has to start at natural log of 2. Right? That's what u is when x equals 2. And as x goes to infinity in this integral, u equals ln of x is, well, limit as x goes to infinity of ln of x is infinity. So u is still going to infinity. The top end point is still infinity. So we'll go from ln 2 to infinity with this integral. Well, integral 1 over u is natural log u. And that'll go from ln 2 to infinity. But as you go to infinity on the top, ln goes to infinity, and the bottom is just a finite point. So this is actually infinity. Diverges, right? Since it's not going to a number. So the series of absolute values diverges. That tells you it's not absolutely convergent. Right? Now, is it conditionally convergent? Look at the series itself. 2, the original series, k equals 2 to infinity, minus 1 to the k, over k ln of 2, is an alternating series, right? The minus 1 to the k and the bottom's positive. Makes this alternating. And the terms are eventually decreasing. Theorem says d is still applied. With eventually non-increasing, I guess is a technical term. This one is eventually decreasing. And then the limit as k goes to infinity of this kth term, of the absolute value of the kth term. I should say the absolute values are eventually decreasing. Eventually the AKs, which are the absolute values, is decreasing. And the limit of the absolute values, these are the AKs, is 0. Those are the two criteria for the alternating series test. Given an alternating series, if AK is substantially less than or greater than AK plus one, in other words, if this is decreasing. And two, the limit is zero, then this converges. So you say, therefore, this converges by the alternating series test. Okay.
Isn't there a third criteria where term has to be greater than or equal to the next term?
That's this one.
Oh, I'm sorry.
I just said decreasing, yeah. So what I mean by that is AK plus one is greater than or equal to AK, yeah, or less than or equal to AK. Yeah, so that one and the, so if they're not increasing and their limit is zero, then it converges by the alternating series test. This book actually calls this non-increasing decreasing. And some other books just call this non-increasing. It's frustrating, but anyway, so if AK plus one is less than or equal to AK and the limit is zero, we should put it that way. Then you get an alternating series convergence. All right, so this one does converge. But if the absolute values didn't, therefore, we get conditional convergence. That was kind of a tricky one. Huh? Anything else that? I should do number 6. I think there's a fair amount of trouble on that. Well, we're always so pressed for time in this semester, but then if we don't do this, I think you learn less than if I push ahead. So it's kind of tough. All right, so hold P3 of X. X minus X squared over 2 minus X cubed over 3 is the third Maclaurin polynomial. For f of x equals ln 1 plus x. And I said, find a bound on estimating the error at x equals 1. Estimating f of x, f of 1 by d3 of 1, this cubic, I guess. So the theorem says that the absolute value of the difference between f of x, p3 of 1 and p3 of 1 is less than or equal to m over, if this is n equals 3, n plus 1 factorial is 3 plus 1 factorial, times absolute value of x, which is 1, minus the expansion point, 0, those are 3 plus 1. In other words, this is x minus, x0, and this is n plus 1 is the theorem. So the theorem says m over n plus 1 factorial, x minus x0 to the n plus 1. In this case, we use P3, so n equals 3. It's a Maclaurin polynomial, so x0 equals 0, and we're estimating at x equals 1, so we put x equals 1. All right, so this is m over 4 factorial times 1 to the 4th is just 1. And now what's m? M is the fourth derivative of the function. It's the maximum fourth derivative over the interval connecting x0 and x, 0 to 1. What can be a bound on that? You compute the fourth derivative, and I guess it comes out to be minus 6 over x plus 1 plus x to the 4th. And so you say, how do you make this? What's the maximum? Well, Right, to make it as large as possible, you make the denominator as small as possible, that occurs when x equals 0. So, it's 6 by putting in x equals 0. And so then you get 6 over 4 factorial, which is 24. Let's fill it down as 1/4. That's the hard way to do it. Nobody did it the easy way. I was very disappointed. What's the easy way to do it? Anybody figure out sense? Yeah, there you go. Yeah. They actually give you extra credit or something. You're getting it now. So the alternative is to say that the expanded series, ln of 1 plus x, which you can memorize, is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And you continue the pattern for positive x, such as x equals 1. You have 1 minus 1/2 plus a third minus a fourth plus blah, blah, blah. Actually, you recognize that's the alternating harmonic series, but in any case, it's alternating with decreasing terms, right? 1 over n is the nth term, plus or minus 1 over n. I guess you'd say minus 1 to the n plus 1. Since these are decreasing, alternating in sign, and tending to 0, satisfying the hypothesis of the alternating series theorem, the error is less than or equal to the absolute value of the next term. So you can look at it and say, oh, the error is less than or equal to the absolute value of minus a fourth, the first term I omitted. And you get the same bound in this case. So that was easier than calculating the fourth derivative. Say, what did I leave out in the next term? So I want to make sure I did that one because both of those ways are nice ways to do it, but this one only works for an alternating series with e equals to 0. Okay, anything else inspiring I should look at? Feel free to come by and see me when I go over at office hours and so forth too. That's it. Whatever. That's the longer than I thought, unfortunately. That was just to scare you guys. All right. All right. Today we want to finish 10.1 and get as far as we can in 10.2. I didn't quite finish 10.1 last time, so that was the parametric equations continued. It's been a while, and we were looking at other stuff. Yes, so I'm going to review just a little bit. Parametric equations continue. Why are these really useful to us? Why do we need them? Here's what they are. For parametric equations in the plane, you can do this in whatever number of dimensions you want. These are equations x and y given as functions of t. X equals x of t, y equals y of t, over t in some interval of numbers. Could be open or closed. Usually we'll do closed in here, but it can be either. But t is an element of some interval is what that says, element of. Those are parametric equations, curve. And if x and y are continuous, it's a curve. I was wondering what a curve is. Here's a curve, and this is the curve given parametrically. Now, we have the additional thing which said if x prime of t and y prime of t exist, you can calculate those derivatives. Then you can calculate the slope of the tangent line to this curve, that is the derivative dy dx, the slope in the tangent plane, right? In the xy plane. But here, I asked you the question, why are these useful? Now that I drew that out there, why do we say where they're useful over things we've already done? In the past, we wanted y a function of x, but last time we said, well, we can make a circle, for instance, at any point by making parametric equations like this. If this is the point x0, y0, and this is a radius r, here's how you can write an equation of a circle going counterclockwise. If I wrote x equals r, a constant, it's the constant radius, cosine t, leave a little space there, y equals r sine t, leaving a little space in there, what would happen? You think of the unit circle in trigonometry, each point at an angle in standard position on the unit circle is cosine t sine t, right? So as t moves from 0 to pi over 2, you go around angle 0, t equals 0 to pi over 2 is the polar angle. Now that's just cosine t sine t. If you go to r cosine t, r sine t, then your r times as far out, and you go around the circle of radius r. So each point on this circle of radius r can be given at the origin by r cosine t is x, and r sine t is y, we said. And then if I just add x0 to each x coordinate and y0 to each y coordinate, then I go around the circle of radius r, it was centered at x0, y0, right? And this just moves this just translates it over x0 and x and y0 and y. So there's how you write equations, for instance, for a circle at any point with any radius you want in the plane using your trigonometry skills, right? You use a unit circle, stretch the circle by a factor of r, and then slide it over, put it centered x0, y0. And now you realize, wait a minute, this is not a function. There's the advantage. I can draw curves that wind around in the plane any old which way, right? And now I can try and do calculus with these things, even though y is not a function of x, by writing x and y independently as functions of t, right? And so I move around the curve. And furthermore, in the circle, you've got kind of a nice thing. T, as you go around, if I make any angle t, is the angle in standard position from the center here, right? So t has some significance, and if you just let t go from 0 to pi over 2 could be your 2 pi could be your interval. That'll take you around the circle once and finish where you started, right here. Right? So there's the kind of things you can do with things like circles and other curves that meander, whatever. And then furthermore, if x prime of t and y prime of t exist, we said that dy dx could be calculated by taking dy dt divided by dx dt, wherever dx dt is 0. So there was the formula for calculating the first derivative. Right? And if this function is differentiable, and it has derivative, also, then you can calculate a second derivative, d squared y dt squared equals d dt of y prime over dx dt is the formula for calculating a second derivative. A little trickier, where y prime doesn't denote dy dt, it denotes dy dx given as a function of t. That's where it's tricky. Y prime means what you just calculated here. Y dx, but you wrote y and x as a function of t, you got a function of t out of this, I'll put out of t. This thing. Can we do one problem on that, or? And then furthermore, you can often sketch these curves by eliminating the parameter we set. I hope you tried some of the homework. We can often, it depends on what it looks like. Sketch the curve by hook or by crook, eliminating the parameter. For example, suppose I said, x equals sine squared t, y equals, this is like one of your homework problems, actually sine t at one. Y equals cosine 2t. And suppose t runs from minus pi over 2 to pi over 2 is the interval of t values. These are continuous functions we know from calculus 1, so this is going to sweep out a parametric curve in the plane, right? Suppose I said, A, sketch the curve. How do I sketch it? Unless you've seen this before, like you saw the circle and you see x equals 2 plus 3 cosine t, and y equals minus 1 plus 3 sine t. Oh, I know that's a circle. X0, Y0 is the center. The radius is 3. You can go right out and sketch it 1, 2, minus 1. Put the center there and make it radius 3 and sketch it about like that. Unless you've seen it and it goes this way, by the way, sometimes people put arrows to indicate the direction of increasing t on these. They'll call that the orientation of the circle as it goes counterclockwise on this one. Often these curves may go forward and back and run over each other. That's okay. It's just, generally, we want it to go around one way for calculus purposes, but we don't always do that. So suppose, unless you recognize the equation, such as here's a circle, it's centered at 2 minus 1 of radius 3, according to our last prescription there. I just leave that and put it next to this. That's a circle. Another example. At 2 minus 1 center, radius 3 is what I wrote. If you don't recognize it immediately, you can sketch by eliminating the parameter. T is called the parameter for the curve, I should say. T equals parameter for the parametric. So it's a dummy variable. You can change it to theta or whatever you like. S. Sketch by eliminating parameter T. Well, you try and think of some relationship you know that eliminates them. For instance, wait a minute, I know the trig identity, the half angle identity, the sine squared t equals 1 minus cosine 2t over 2. This is actually the half angle identity squared, right? If you square the half angle identity, you get that. And now sine squared is x squared, so this implies that x squared equals 1 minus cosine 2t is y, 2. And now that I eliminated the parameter, maybe I can sketch that, right? If I think about it, this is equivalently 2x squared equals 1 minus y, or 2x squared minus 1 equals y, minus y. Finally, y equals minus 2x squared plus 1. Then I want you to be able to sketch these, right? Use your graphing techniques. I don't think I learned these all that well when I finished my PhD. I mean, I knew it sort of, but you find out when you start to teach this stuff, being able to graph these is really useful. How do you sketch a general, and you learn this in algebra. You write in the canonical form sometimes, y equals a times x minus h squared plus k, right? Then it's a parabola centered at hk, and with this a that's sort of the stretching factor. That's one way to do it, and that's a real good way. It, however, comes from this kind of derivation. You can say, well, it looks like y equals x squared. Here's this. Except I stretched it by a factor of 2. Here's y equals 2x squared is just stretched. And I like to put these easy points on here. Minus 1, 1, 1, 1, and 0, 0, 3 easy points on it. A lot of these basic functions, you'd be surprised how many of them go through points like this. Minus 1, 1, minus 1, minus 1, 1, minus 1, and 1, 1, and 0, 0. It's really surprising how many- when you start to think about it. Okay, but here's y equals 2x squared, and I'm gradually building up towards this. Well, I'll leave this out. If you really had to graph it that way, that's just as good and faster. This is for in case, this is deriving what you do this way. This stretches it by a factor of 2. Now it goes through the point, it doubles every y coordinate from this one, right? So minus 1, 2, 1, 2, but this one stays at 0, 0, because doubling y equals 0 is still 0. So I go from here to here. Now if I can zigzag, trying to save these things, but maybe I can't. Now what does y equal minus 2x squared look like? Well, it just turns this one upside down, makes all the y coordinates negative. So that makes the same shape as that one. This one stretches all these points by a factor of 2. This one flips it upside down. There's y equals minus 2x squared. Now it goes, just makes every y coordinate negative. Minus 1, minus 2. 1 minus 2, and 0, 0. But we've got y equals minus 2x squared plus 1. Well, that adds 1 to every y coordinate and raises it by 1. So you can now sketch this by putting it up 1 and you just add 1 to every y coordinate and get 0, 1. Minus 1 minus 2 becomes minus 1 minus 1. And 1 minus 2 adding 1 to the y coordinate gives 1 minus 1. So there's what it looks like. Y equals minus 2x squared plus 1. You can do these kind of little tricks for graphing parabolas and circles and so forth. And it's really a nice way to figure those out. So what we've shown here is that these parametric equations give you this parabola, y equals minus 2x squared plus 1. And here's a sketch of it with 3 really useful points, easy ones on there. And then the thing is, though, it doesn't necessarily sweep out the whole parabola, right? So what you have to do is figure out which part of the parabola does it sweep out. They ask you for the orientation on this thing. Which way does it go? Does it go around this way or this way? And like I say, some of them go back and forth, depending on how you wrote the parametric curves. There will be later in the upcoming sections a nice way to do that. So I don't want you to fluster too much over that at this point. Instead, say, well, if t goes from minus pi over 2 to pi over 2, and x is sine t, then when t equals minus pi over 2, sine of minus pi over 2 is minus 1. So x goes from minus 1 when t equals minus pi over 2, and sine continues to increase, right? If you put t versus sine t, and you go from minus pi over 2 to pi over 2, sine t goes from minus 1 to 1, and it's continually increasing. So x increases from minus 1 to 1, increasing all the way, right? You go up this sine curve, y equals sine t. And as t goes from minus pi over 2 to pi over 2, y, or in this case x, maybe I just put sine t, x goes from minus 1 to 1. And so what happens is you can think, what part of this curve does x go from minus 1 to 1? Goes from here to here. Here's an easy way to figure it out too. Just start by putting in the initial parameter. Trace these at the last moment. That's Murphy's law, right? At t equals minus pi over 2, just plug it in and find out what the starting point is another way. X equals minus 1, sine of minus pi over 2. Y equals cosine of minus pi is minus 1. So when you plug it in, you get x equals minus 1, y equals minus 1. You're starting. Oh, it's this curve. Yeah, this one right here. Oh, it was on this curve for a second. So you're starting right at that point here. And then at the end, x is increasing all the way, right? Because that's what we said here. As t increases from minus pi over 2 to pi over 2 sine t, which is x, increases from minus 1 to 1, never going backwards. And then at let's get rid of this one. All right. Hope this isn't too much review. At t equals plus pi over 2, the ending point x equals sine of plus pi over 2 is 1, and y equals cosine of 2 pi over 2 is cosine of pi is minus 1. So it finishes at x equals 1, y equals minus 1, which is this point. And so evidently, it's going, since x is increasing all the way, it must be going around like this. So we draw the arrow like that and say that's the orientation from this one to this one. And it's only this piece of the parabola. So you can eliminate the parabola and find out what curve it's constrained to, but then you have to think about what are the endpoints and what's it doing in between to graph it out. It has to do this whole thing because these are continuous functions, so it moves along a continuous curve here. From the one point to the other, just once because x is increasing all the way, right? So you can argue that for now, and later we'll have a better way to figure out which way it's going. All right, now that being said, we said now we can start to do calculus with these parametric curves. That's one of the advantages, right? You have something weaves around in the plane. Now you can find slopes of the tangent plane to these more exotic curves, right? You can draw a hydra or something. All right, so put part B. What is dy dx when we're at the point that t equals, let's say, pi over 4? What is dy dx, sorry? What is the slope of the tangent line? This is tracing out this parabola in the xy plane, or this portion of the parabola. What about the point where t equals pi over 4? What's dy dx? Well, we use the formula here that I used to write. Oh, there it is. Dy dx is, right, it's just like fractions, dy dt over dx dt. So you take from the parametric equation through that x is cosine t, root of sine t is cosine t. Derivative of cosine 2t, you have to use the chain rule, right? Derivative of cosine is minus the sine, times derivative of 2t is 2, so it's minus 2 sine 2t. Oh, I put it backwards? Yeah, thank you. Yeah, minus 2 sine 2t over cosine t. Derivative of y on the top, derivative of x on the bottom. Thank you. And so this is the slope of the tangent line at any t along the curve. And now in particular, at t equals pi over 3, the slope in the xy plane is dy dx. You just plug in t equals pi over 3 minus 2 sine 2 pi over 3 over cosine pi over 3. It was over 4, sorry, pi over 4. And cosine pi over 4 is square root 2 over 2, you recall from the unit circle. Sine of pi over 2 is 1, so this is minus 2 over square root 2 over 2. Gives us what? Minus 4 over square root 2, or better, minus 2 square root 2. There we go. So there's the slope of the tangent line when t equals pi over 3. And then one of the problems asks you, what's the equation of the tangent line at this point? So let's see, find the tangent line to this parabola at that point. Well, you've got the slope at that point. Now you need the point, so you just plug it in. So x was cosine, sine t, so it was sine pi over 4 when you plug pi over 4 into x, and y was cosine 2t, so it'd be cosine 2 times pi over 4. And so this is cosine of pi over 2 is 0. Sine pi over 4 square root 2 over 2. So this is the point, x equals square root 2 over 2, y equals 0, right here. That's the point of tangency. Once you have the point of tangency, you can write the equation of the tangent line of y minus y0 equals m times x minus x0. Is that one familiar for calculus 1? Find an equation of a tangent line. One way to do it is to write the point slope formula. Y minus y0 equals m times x minus x0. Goes through the point x0, y0 with slope m. We have the slope, it was minus 2 square root 2. We have the point, it was square root 2 over 2, 0. There's the equation of the line. Then you can simplify it as y equals minus 2 square root 2x. And then when you multiply these, let's see. These cancel and you get minus 2. Oh, no, let's see, that's okay, yeah, okay. So there's the equation of the tangent line. You can do all those kinds of things. Then you can say, what's the second derivative at that point? We didn't get to do an example on that last time. D, find d squared y dx squared, the concavity at this point where d equals pi over 4. So you say the second derivative is a little harder to remember. It's not just fractions. It's derivative of y prime that you just calculated with respect to t over dx dt. Right? Well, y prime we calculated right here. We can simplify this a little bit if you think about it. All right. Sine of 2t, if you remember from trigonometry, the double angle formula is 2 sine t cosine t, right? Once you write that out, oh, gee, the cosine t's cancel. So this is just minus 4 sine t. Is another way to write the derivative. At any t, this is the slope of the tangent line. This will be easier to take the derivative up here. So y prime is this one. Y prime means dy dx here, not dy dt. Oops. Dy dx is the notation. And written as a function of t, so I can take d dt of it. So what we found out that y prime, oops. Yeah, I wrote it wrong. Okay. Oh, I wrote this wrong. This is supposed to say dy dx equals dy dt over dx dt. The slope of the tangent line dy dx, that's what I was trying to find, is dy dt over dx dt is minus 4 sine t. So now I'll put that in for y prime. And I've got d minus 4 sine t dt on top, and then x was sine t. So derivative of sine t, well, derivative of sine t. And so I just get minus 4 cosine t over derivative of sine t is cosine t. And I find out actually the second derivative is minus 4 regardless of t. That makes sense. A parabola has constant concavity, right? Constant second derivative. Constant second derivative, this one is minus 4. You could figure it out from taking the derivative here, right? Take the second derivative So this one where you eliminated t and double check it, right? So you can also get it from here. But if you can't solve, eliminate t and solve for y as a function of x, you can still calculate second derivatives using this formula. Second derivative is dy prime dt over dx dt and get the same answer. Once taught a class over in the nursing building. It's terrible for math. They've got these little tiny boards over there. These are graduate classes. Writing, any questions? Erase it all. Any questions? Or is it 4 boards later? Any questions? And 3 or 4 boards back. We had long problems in math modeling, and it was terrible. And I have to do it here. I ran up 2 boards. Any questions at this board or the board back? Sorry about that. This is sort of a comprehensive problem. I think it's a real good one. It shows you all the tricks on those. All right. Good, because I probably can't reproduce it. All right. Now we want to carry that a little further. This is very cool, this next part, I think. Shows you how this extends your previous capabilities. Remember seeing arc length before? Got those two? We can redo arc length but better. So we're going to do a whole bunch of calculus techniques. One was find the derivative, another one find the second derivative, and then find tangent lines. Now we'll do arc length. And here's what we have. It's very similar to what we did in calculus 1, but the curve no longer has to be y a function of x. Here it is, a parametric curve C given by x equals x of t, y equals y of t, for t in some interval. Let's say an element of some interval I of real values. And maybe it goes around this way, it doesn't matter. But what you do is you think of how can I estimate the length of the curve? If I start from this point, let's do it this way. Let's say t is an element of the interval from t0 to t1 at that closed interval. Then this one would be x of t0, y of t0. And this one will be x of t1, y of t1. Okay, so it goes from t0 to t1. Oriented this way. What we can think of doing to estimate the length of the curve is we can start here and take a whole bunch. Oh, not T1. I'm sorry. But to be consistent with the book, let me call it A and B. This would have really messed me up when I was a student because I always used pen and I couldn't erase it. All the engineers did better; they could erase it. Let's call this x of a, y of a. This will be less confusing, even though I confuse you for a moment. X of a, y of a, x of b, y of b. Then it'll look like the book, and all my notation will be better. All right, so we're going point A to point B. All right. What's the length of that curve? Well, we'll call this also a equals t0, and we'll partition this interval AB into subintervals with A equals T0 and B equals Tn. We'll make it n intervals. T0 to T1, T1 to T2, n subintervals down to Tn minus 1, Tn. Then we continue going from here, x of a, y of a, or x of t0, y of t0, to x of tn, y of tn. And in between, we stop at a bunch of resort places here. X of t1, y of t1, x of t2, y of t2, and we'll take, to estimate the length of the curve, we'll just take the sum of these line segments whose length we do know between the points. And so this, here's maybe x of tk minus 1, to x of tk, some intermediate point. I'm sorry. Let's go s of tk to y of tk, and x of tk plus 1. I guess I want to try to be consistent here. Put minus tk minus 1, tk minus 1, and tk and tk here. So 2 consecutive points in the middle of the interval arbitrary. And what we can do is call this length here L1, L2, Lk for the kth interval from tk minus 1 to tk. I'll go from 0 to 1 here, and then k minus 1 to k on the kth interval. And here's Ln, the length of the last line segment. And we'll say that the length of the total arc here is approximated by the sum of the Lk's, which are straight line segments, so I know how to compute their length with the distance formula. K equals 1 to n subintervals, right? This is worth deriving here, because it gives you good intuition. Now, what is the length of each subinterval? K equals 1 to n. Well, it's Pythagorean theorem, right? You make a little right triangle here. We put this Lk on the other side. Now this one is, let's see, y of tk minus y of tk minus 1 absolute value. Absolute value of, I don't have room to write the whole thing. Absolute value of y of tk less y of tk minus 1, the change of y coordinates. And this one has length x of tk minus x of tk minus 1. So that's the length of the two legs, and now the hypothesis is the root sum square of those by the Pythagorean theorem or the distance formula is now the difference in the x coordinate squared. This one squared, you can grab the absolute value since you're squaring it. It's x of tk minus x of tk minus 1 squared. That's the square of this one. Plus y of tk minus y of tk minus 1 squared is the square of the other one. So we're adding all those up. Now we can also let delta tk be the kth increment in t. It can be tk minus tk minus 1 following your calculus 1 notation, right? Delta tk is just long 2 letters with a subscript to indicate this difference, the length of the kth subinterval of t. Then this can be written as sum k equals 1 to n. And inside I could divide by delta tk squared, so I could write x of tk minus x of tk minus 1 squared over delta tk squared plus this one over the same, y of tk minus y of tk minus 1 squared for delta tk squared. So inside I divide the whole thing by delta tk squared, and outside the square root I can multiply by delta tk and cancel it, right? Because this would come inside this inside the square root is the square of this and cancel these two. So that's the same just by algebra. And now what happens if I let well, let's rewrite this. Maybe I should write one more step here. So this is the sum k equals 1 to n of the square root of x of tk minus x of tk minus 1 over delta tk squared plus y of tk y of tk minus one over delta tk squared multiplied by delta tk outside. And now you remember something called the mean value theorem for derivatives. What did that say? For the mean value theorem for derivatives. So if you had a derivative like dx dt between 2 points, tk minus 1 and tk, see if the picture looks familiar, tk minus 1 to tk, the slope of the secant line, which was, right, if I call it the x-axis, the slope of this was x of tk, the change in the vertical coordinate, minus x of tk minus 1 over delta tk, this difference of these two, tk minus 1. Right? The rise over the run was the slope. Right? Here's the rise, here's the run. And the mean value theorem for derivatives said there's some point in the middle, tk star, maybe more than 1 point, but at least 1 point, where if you took the slope of the tangent line, it was equal, right? So that x prime of tk star was the same, was equal to this. That's the mean value theorem. I'll put it MVT for mean value theorem for derivatives. Somewhere in the interval, there's a point for it. This is for a function that has a continuous derivative. If the derivative is continuous, this holds, it says. So we assume that x prime is continuous when we do this. Then we make this slope equal to this slope of the, oh, but wait a minute, that's what we have here. So if I can erase this and just remember that we're approximating the length of the curve by the sum of the lengths of the line segments. We can say this is actually equal to the sum k equals 1 to n of the square root of the x dt at some point tk star in the middle between tk minus 1 and tk squared plus dy dt at some intermediate point tk double star, it can be in general different squared, times delta tk. And these are both continuous by assumption. These two derivatives. And there is our estimated arc length. And now we say, suppose we let n, the number of increments, go to infinity. Got what? We'll say L is going to be then exactly equal to the limit as n goes to infinity, the number of increments goes to infinity. This will be a definition, actually. We'll define the arc length to be the limit of this quantity, sum of the LKs. All right. The idea being for a smooth curve, a curve with one continuous derivative, you think of taking more and more line segments, right? More and more line segments and adding them up. Maybe in the limit, as the number of line segments goes to infinity, you'll get the length of the curve. We're going to define it that way, actually. And there's good reason for that. If the derivative is continuous, then it doesn't matter how you break it up into increments, as long as the width of the widest interval goes to 0. This always gives the same number, so it has to be what you want to define to be the arc length. So we'll say we'll define the arc length to be the limit as the number of line segments goes to infinity. And implicit in this notation is the width of the widest subinterval has to go to 0, even though that's not explicitly here. Some books will say limit as the width of the partition. In fact, maybe this one does it, goes to 0. And that means the same thing, meaning the width of the widest subinterval goes to 0 and the number of them goes to infinity. I'll write this because it's easiest, but any of those notations, it's implicit that the number of intervals goes to infinity with the width of the widest one going to 0. Is now the limit. Well, this L, some of the LKs was this, right? Limit K goes to, n goes to infinity of the sum k equals 1 to n of the square root of dx dt squared plus dy dt squared dt, where these are evaluated at some intermediate point, dk star, dk double star. What is that? Not c, delta tk. What is that? Recall this, if I wanted to take a definite integral from a to b of f of x dx, the definition of the definite integral was the limit as n goes to infinity of sum k equals 1 to n f of xk star, where xk star was any intermediate point whatsoever in the kth interval, delta xk. That looks curiously familiar, doesn't it? In fact, it's exactly the same thing. It's just that f, except that x is the variable instead of t, the independent variable. And the f in here is this. By definition of the definite integral, this is actually equal to the integral, since we have the same interval from a to b. It's equal to the definite integral from a to b of this function, square root of dx dt squared plus dy dt squared dt. And this notation means this, according to our definition, with one very slight sleight of hand in here. Do you see the sleight of hand? Mathematical magic here. I mean, one additional assumption. This isn't strictly the definition, because this one was evaluated at tk star and this one is evaluated at tk double star. In general, there are two different points. There's a theorem that says even if they're different points, it adds up to the same as if they're the same point. And when you apply the theorem, it says you can use different points and it still adds up the same. Then this is equal to the definition is equal to this. So there it is. There's the derivation of what we call arc length. And we'll just define it that way with the idea that that's exactly what you want for a curve with a continuous root. Just like when you do the area under the curve problem. Remember in calculus 1, how did you define the area under the curve, right? Well, it was this thing, right? And the idea was you went from a to b, you broke this up into n subintervals. So there's your y equals f of x. And if you broke that up, you could use inscribed rectangles where you took the lowest height on the interval, like this. And if the limit as the number of intervals went to infinity, you got a number, right? This always became a number. Or you could use circumscribing rectangles. You could use the highest point at each interval and add up the areas of the rectangles and take the limit as the number of rectangles went to infinity. What happened? If you let the number of rectangles go to infinity with inscribed rectangles or circumscribed rectangles, you got
The exact same.
the exact same number. These add up the same, whether you circumscribed or inscribed in the limit. As long as f is continuous, it gives you the same number. And so we want to define that to be the areas. The idea that if they circumscribe and inscribe, take the limit, get the same number, that must be what the area is. Same thing with the arc length, because regardless of how we break it up, we get the same number. We'll define that to be the arc length, but it's what it has to be, because it's what everything is becoming closer to, no matter how you increment the thing. It always adds up to the same number, provided that this thing is continuous. Provided that the dx dt and dy dt are continuous. So there's the derivation. I think it's worth seeing. It reminds you of a lot of important features. Except I used up all my time now. So this is the theorem that we derived. I'll write it down. Hence, not a theorem, the definition we derived. We'll say that the arc length is equal to the integral from a to b of square root of dx dt squared plus dy dt squared dt for x of t, y of t, smooth. But you have to be careful of that word mathematics. Sometimes it means as many derivatives as you need are continuous. In our case, we'll mean one derivative continuous. also called C1 function. So one continuous derivative in this book on the integral AB. So that's all you need is one continuous derivative because you needed the mean value term to apply. And this will be the R. Now, do I have time for example? Let's see. Have to do a really easy one now. Here's an example. Suppose I have x equal 2 cosine t, y equal 2 sine t. What is that? That's a circle of radius 2 at the origin, right? And if t runs with polar angle t. If t runs from 0 to pi, then this is the semicircle of radius 2, right? This is the unit circle from trigonometry. We multiply by 2. It's a circle of radius 2. Goes from 2, 0, minus 2, 0. We know t is the polar angle from trigonometry. We just double all the coordinates. So we're moving around this way. What is the arc length of that curve? All right, so the arc length is just the integral t going from 0 to pi. Right, that's a to b. Square root of dx dt. Well, that's derivative of 2 cosine t is minus 2 sine t squared plus dy dt squared. Well, that's derivative of 2 sine t is 2 cosine t squared. All right, so dx dt squared plus dy dt squared, square root, integrated. What you find in practice is this thing hardly ever gives you an integral. You can do that. Square root just makes it real difficult to do the integral. You're not in terrible trouble because you can always go to your numerical analysis class and estimate this thing as accurately as you want in practice. So all hope is not lost. But in the book, they'll give you cook problems like this one because what happens? Integral from 0 to pi of 4 sines, square root of 4 sine squared plus 4 cosine squared dt, and I can factor out the 4 and call it 4 sine squared plus cosine squared. Right? Oh, that's just 1. So this is actually just integrating the square root of 4 or 2 from 0 to pi, and I get 2 pi. Sure enough, the arc length of half the circle, right, the circle should have circumference 2 pi radius, which would be 4 pi, and this is half of the circumference. So sure enough, it's just what we expected from our formulas. So there's a simple example. Try the homework. I don't know if I gave it all to you last time. Let's do 10.1. I said 3 to 17 odd, 45 to 53 odd, 65, 57, and 75. 75 is actually surface area. I think it's really easy, but we haven't covered it yet. We'll do that first thing next time, hopefully. And then we'll be which I thought I was going to do today. But thank you for your patience. I'll see you next time.